We ran into a pretty big snag and enormous setback, and it was predicted by PSpice, which is unfortunate. I didn't know what it was telling me at the time, but our static NMOS high current switch is not going to work in this application, and I didn't realize that at the time. I thought because it was passing current that it would work, but there's problems inherent in what we're trying to do. We have a bunch of 5-volt power supplies chained together, so effectively, even though it's only 5 volts, we are high side switching because we are switching right from the source to the load. And getting NMOS to high side switch is not that simple. In this example, it's not that simple. In an H-bridge, it's a little bit simple, more simple than this because we're not load banking here. But because we're trying to make a bank switch, we have to have isolation diodes to isolate the body diode. Otherwise, they conduct to each other. So that was, yeah, that was minor, that was trivial. And then because it's high side switching, we have isolated gate drives for each one, and we have isolated power for each one. We anticipated all of that ahead of time, but what we didn't factor in was the fact that we're getting 30% dropout in load power. So that's a big setback. We went back and we checked out the PMOS. It's a little 40 amp PMOS here. I think it's 40 amp. It's 40 amp. No, it's 20 amp. 20 amp. It works great. And you wouldn't have a problem with body diode with them in parallel or bank switching or any of that. The body diode is going to prevent the back current flow. But at the time, the trouble was locating 100 amp PMOS, and said, I'm just going to look for an NMOS and high side switch it. So a big part of this journey is the learning part, and we learned that it's not really a problem to parallel PMOSes because they have a positive TempCo. The PMOS that's drawing more current will heat up, and then its resistance will increase, so it'll start passing less current. So theoretically, over a long time, the two will balance. They will start flowing the same amount of current. So one will get less current, and the one will get more, and they'll stabilize. So we didn't have to go with a single MOSFET designed for these are 192 amp piece, but it wasn't necessary to go for such a low RDS on and 192 amp specs. We could have paralleled some 20 or 40 amp PMOS. It would have been fine. Going forward, the whole goal here was arcless switching because relays wear out over time. But this project has gone on for a long time now. We're looking after winding transformers over and over again, trying to get 30 amps out. The current requirement's very high. 30 amps is quite a bit of current to get out of a transformer with minimal losses. So that's somewhat difficult. You've got to have a pretty good transformer for that. you can see what we've done here. These are 5-volt 50 amp power supplies, and they'll give us about 40 amps fairly solid. We're still going to try PMOS high side switching. This should be fairly easy to implement, but we're going to take that offline from this project. Sadly, I'm going to go with relay, and the automotive relay is the cheapest solution, and it's field replaceable. Didn't want to do this, but these are 80 amp relays, and we're only switching 35, maybe 40 amps max here. So that should be minimal impact to the relays. It should not impact their life too much. They're meant to handle 80 amps continuous. I didn't want to do that because they still arc, because this is DC. They are automotive, so they're meant to arc. If they need replacing, they're replaceable. They're like 13 bucks a piece. It's not a big investment here. But to go with a Potter Brumsfield or something that's name brand, that's going to handle 80 amps, is an enormous form factor, and it would not be permissible in the space that we have here. Of course, this is going to eventually become rack mount. That's in the future. Since we don't need so many voltages, we have isolation because of relays. That kind of invalidates the need for the transformer with 19 taps. So that was, unfortunately, that was wasted time as well. We'll probably try to find, because we bought two, we'll probably try and find the other one that has, I think, 4 taps on it, and this system will probably be fine with that instead. Because we need 2 supplies for the control system, and the control system is going to be 12 volts plus and minus, and the relays can be run off of one of those. And then we'll need power for the meter units, and those should be isolated, but we're not there yet, so we'll get there when we get there. We could run a small inverter or some other power supply off of the main 12 to get us isolated, but we'll see. The goal is to keep it field replaceable, field serviceable. We don't want the customer to have to return this to us. We want it to live a long time. The 5-volt 50 amps are Chinese switching power supplies. If they die, you can take it out and switch it in. Shouldn't be a problem. The box size may change over time. That might be a problem. We don't know yet. So today the goal is to get the relays banked in and see if we can get tap switching working with relay. Didn't want to do this. The whole goal of this, the whole point of this adventure was arcless switching. We were trying thyristor, MOSFET, trying all kinds of different ideas to get around the bank select in a novel way, but it seems like we have to go back to old practices. So that's where we're at for now.